Hello, everyone. So I have, I guess, two announcements to make. First, the quiz will be released sometime after the class, and the deadline will be 11 a.m. On Friday. And then the second announcement is about your project. So lab 3, the deadline is next Monday, so please don't forget the deadline. There won't be any extensions, so try your best to make it to the deadline. Okay, so I guess that's pretty much what I have for announcements. Let me get started. So today we're going to talk about real-time systems. So we'll start with some definitions, and then we describe what are the desirable properties that a real-time operating system has to have, and then we compare what we have in general purpose operating systems and what we want in a real-time operating systems. And that comparison actually is very informative. So once that is done, we get to the main topic of this lecture, which is real-time scheduling. So we'll start with a uniprocessor real-time scheduling, and then we talk about multiprocessor scheduling in a real-time system. Okay, so let me get my video out and let you just see the slides. Okay. So a real-time system is defined by its temporal aspect as well as its functional aspect. So what we want from a real-time system is a real-time operating system is its timeliness, its ability to deal with the temporal aspect of a system. So usually when we talk about temporal aspect, what we really mean is that we have tasks in the system that have deadlines and strict time constraints. So in those systems, when you talk about performance, you no longer talk about average performance. You don't talk about average response time. All you care about is, have you or haven't you met the deadlines? So each individual response time becomes important, not the average. And a key property of a real-time system is its predictability. So everything in a real-time system has to be predictable. Please note the difference between predictability and being fast or having high performance, because you still can have high performance and not be predictable. So what we really care about in real-time system, this comes again and again and again up. So what we really care about is predictability. Can we predict, can we estimate how long each task, each job takes in our system? So there are different types of real-time systems. We have soft real-time systems. So in these systems, you have a deadline, but you might fail to meet that deadline. And if you do so, then nothing dramatic happens. So it's best depicted by this picture. So in this picture, what I have is on the x-axis, I have the deadline, so basically the time. And this point is basically the deadline of my task, let's say. And on the y-axis, I have the value and usefulness of this task. So if I finish my task anytime before its deadline, I get full value out of this task. If I miss the deadline, the value I get out of this task starts diminishing linearly until it gets to 0. And after that, if I finish this task, there is no value in finishing it. Then you have firm real-time systems. So in this case, you have a firm deadline, which if you miss, then you won't get any value out of finishing the task. So same as before, you have a deadline. If you finish your job anytime before the deadline, then you get the full value out of it. If you miss the deadline, then you get 0. And finally, we have hard real-time systems. So these systems, again, like the previous ones, have deadlines. But if you miss the deadline, something really bad happens, and you start getting negative utility afterwards. So if you miss the deadline, now there is a penalty associated with it. So if you look at a spectrum of systems, you could potentially put them somewhere between not a real-time system to a hard real-time system. And usually systems are somewhere in between. So in the middle, I have the soft real-time system, here hard, and then no. Basically, if you're doing computer simulation, you know, those who work with microbiology, with chemistry, they want to do simulations. Maybe like you want to do, I don't know, simulations of structures in physics, whatever that be. You really don't have really a hard deadline. So these computer simulations are usually not real time. Then you have user interfaces. Here you get to see some notion of deadline, some notion of responsiveness is important, but it's still not a big deal if one time you click on a link and it takes a little bit more time. Nothing really bad happens. So here in the middle, I have cruise control, for instance, is a soft real-time deadline, a real-time system. You want to be responsive, you want to have a deadline, but even if you don't hit your deadline, nothing really bad happens. You start missing some value, and then at the end of this spectrum, you have something like electronic engines and flight control. So in those cases, if you really miss the deadline, bad things could happen. There are lives on the line in these systems. So this should give you a good perspective on what we really mean by soft, hard, and firm real-time systems. Now, in a series of slides, we'll talk about different aspects of operating systems that we've seen, and one particular aspect that we haven't yet seen about memory management. And we'll compare how general purpose operating systems deal with those aspects and how that way of dealing with those aspects is inadequate for real-time systems. Generally speaking, multitasking and scheduling is one area that you see the huge difference. So usually when you're talking about multitasking and scheduling in a general purpose systems, you're basically talking about throughput. And you want the highest performance you can get out of multitasking and scheduling. So the way that we so far talked about it was we provide system calls to the user so that user can use those system calls to create tasks and threads to achieve what it wants. But as we will see, system calls are detrimental and harmful for real-time systems, and they really don't fit well with the mission of a real-time operating system. Now, the same goes with interrupt management. the same that the way that we deal with interrupt management in a general purpose operating system is through interrupt handling, which is basically what you're doing for a lab 3. And what what interrupt handling does is that it's kind of like the highest priority thing in the system. When an interrupt happens, you hold on to whatever you were doing and you start dealing with that interrupt. Now you could imagine what would happen if what you were doing was something related to the electronic engine or the flight control. And then the interrupt handler takes some time, and that could potentially lead to missing the deadline for that hard real-time task. So that's another aspect that we'll see differences between general purpose operating systems and real-time operating systems. The other area that is also important, and we will see in these slides going forward, is how we basically deal with inter-process communication and synchronization between tasks. In a general purpose operating systems, you have a critical section, somebody locks a mutex, and everybody else has to wait for that somebody. Now, in the context of real-time operating systems, you will have to deal with some priorities. So some tasks have higher sooner deadlines than others. Some tasks have higher priority than others. And you really don't want these high priority tasks to be waiting for low priority tasks or tasks with deadlines that are far in the future. So you want to deal with priority inversion, something that you really don't deal with in a general purpose operating system. We'll talk about all of these and some more. Now, what are the desirable properties of a real-time operating system? We start with predictability. So we want to make sure that we can meet all the deadlines. We want proofs and guarantees that all the deadlines, as long as they meet some, some criteria, then we can definitely meet them. So we want to say for instance, if the utilization of the system is less than 100%, if your system is not overutilized, then every task will meet its deadline. That's basically predictability, what that means. We want a real-time operating system to have timeliness, meaning that it has to be able to deal with time constraints that tasks could have, hard, firm, or soft deadlines. We want also fault tolerance, as you could imagine, for instance, in an engine, in an electronic engine, you don't want a fault of a wire there to crash the whole engine. You want to isolate the fault and then deal with it in isolation without crashing the entire system. And you also want to design for peak load, and you want maintainability, things that actually matter a lot in real-time systems. So let's start with microarchitecture. We'll start with hardware, and then we make our way up to software, things that are a little bit different from general purpose systems and real-time systems. Now, one aspect of processors is I/O devices, your input-output devices. So we talked about DMA at the beginning of the course when we were talking about, I think it was the second lecture where we talked about 4 main concepts of operating system, where we talked about DMAs. So usually I/O devices share a same bus with the CPU when it comes to communicating with memory. So if you remember, I'm just reminding everyone what DMA was. So DMA was when the CPU would let a device to take care of data transfer without CPU being involved. So that was good in a general purpose system. It would give a really good performance. But what is negative about it in real-time system is that with DMA, I/O devices could slow down the CPU. And the reason for that is the fact that both of them share the same bus. So if I/O devices are using that bus a lot, then the CPU, which potentially could be running high priority tasks, will be backlogged. So one way to deal with this is to time slice the bus. So basically, what we did with something like round robin, where we had time quanta, and then each task would get its time quanta. You could do the same thing with the bus that connects both CPU and the I/O devices to memory. So you can have time slices. If you do so, then CPU knows how many time slices it has on that bus, and it could predict how long it takes to do its tasks. So there is no undeterministic aspect to it, no stochastic aspect to it. Because previously, if they share, then we don't really know what's going to happen with I/O devices. Maybe you get a lot of packets through your network card, and at that particular moment of time, the bus becomes really overloaded and CPU gets backlogged. But if you have time sharing, you have time sliced the bus, then you have guarantees of how much at least you get to use the memory bus. The other aspect when it comes to microarchitecture is caches. So we'll have a whole lecture on caches, but hopefully by this time you all know what is the main purpose of caches. So we have caches to speed up memory operations. We want to cache the already seen data very close to the processor, so that the next time that I need to access that data, I have it very close to the processor, and I can access the data very fast. Now the problem with cache, this is perfect for general purpose systems because it speeds up everything. But the bad thing about it for real-time systems is that it introduces some non-determinism. And the reason for that is that you really don't know which data is cached and which data is not cached. So something very similar to a non-uniform memory accesses that we talked about previously happens here. So when you access a memory block, it could be cached. In that case, the execution time of that load is really, really fast. Or it could be not cached. In that case, you have to go all the way to the memory to bring it, or in some cases, you have to go to the disk, and that takes a lot of time. So there is non-determinism, and that is detrimental and harmful for a real-time system. One solution for this is to just get rid of all the caches. Don't use caches. It's pretty dramatic, but if you really are dealing with real-time systems, this is the way that many people go. So you could design your own processor, or there are actually microprocessors that you could use without caches, so that you don't need to deal with that non-determinism. Okay, so now let's move on to some interface between software and hardware. In particular, let's talk about system calls and interrupts. So as I alluded in the beginning, system calls are the way general purpose operating systems provide services, right, to the software. Now, usually, as you have seen it in your lab, system call handlers are non-preemptive. So you disable interrupts at the beginning of them, and you enable interrupts when you return from them. And while you're doing it, you're basically disabling all the interrupts. So I got a question. What if you always assume a cache miss, and if you happen to get a hit, you just complete the task early? Okay, so this is a good question. This is true. So you could potentially have worst case guarantees for your tasks, and that is fine. The problem, though, is the non-determinism that it introduces. So although you might have be able to prove that in worst case I can deal with the deadline, but it actually introduces non-determinism, and that could be harmful if you have a chain of tasks, for instance, that are related to each other. So you have to first do this task and then next task and then next task. Maybe they share a lock or mutex. So, and then if you allow each one of them to have worst case and best case and something in between, then analyzing the workload as a whole becomes almost impossible. So maybe for that one task, you could guarantee stuff, but if you have a workload with so many tasks, and each one of them you allow it to have a range of execution time, then it's almost impossible to guarantee anything for that workload as a whole. That was a good question. Okay. So now this way of dealing with system calls, going back to the system calls and what we were discussing, is fine with general purpose operating systems where we don't have any deadlines. But if you actually have a real-time system with deadlines, then that could potentially cause problems. Let's say your task calls onto a system call, and let's say for whatever reason that system call takes some time. Now, while the system call is running, let's say another task comes in with really high priority, with a very close deadline that you have to meet. Now, at this point, since the interrupts are disabled, there is not much you can do in reclaiming the processor and giving it to the newcomer. And that could cause a missed deadline and unpredictability, really, in your system. So one solution, a possible solution, is to, well, let interrupt handlers to be preemptive as well. And in essence, that doesn't introduce a lot of problems. So it's doable. And it's the way to go if you're designing a real-time operating system. Now, things are a little bit more complicated when you talk about interrupts. System calls are synchronous mode transfers. They are initiated by the processor, by the process that is running, by the task that is running. But interrupts come asynchronously from external events that happen in the system. Now, with interrupts, you really cannot make them non-preemptive. We talked about all sorts of issues that could happen if you let the interrupts to happen inside each other. You might end up not dealing with the first interrupt that happened because further interrupts come and then they all preempt each other. So that's not an option here to make them preemptive. We can't do that. So what can we do then in this case? So the same problems, I'm not going to explain the problems again. I mean, you could imagine why having non-preemptive interrupt handlers would cause unpredictability in your system. Let's say you're running your task and then an external event happens. So based off of how many events happen during your execution time basically changes. And because you cannot control external events, then the execution time of your task is basically not predictable. Now, one solution is to just disable all the interrupts altogether. Don't let them even happen. Only keep the timer interrupt so that you get to, schedule tasks as usual. And you still need to deal with I/O devices, right? So what you can do is to just move all the responsibilities of dealing with I/O devices to each individual task. So any task that needs to deal with I/O, they deal with I/O individually. So just as an example, to make this connection with the project that you're doing right now. So in our project, we have two tasks that deal with interrupts, sort of. So it's kind of isolated between those two tasks. Anybody else, all the other tasks, although they can indirectly use the terminal, but they don't need to know how to. So the entire logic of dealing with devices goes to particular tasks. In this method that I have here, solution 1, you have to enable every task to individually be able to deal with I/O devices as they wish. So if you have a task that deals with network, this task has to have all the drivers logic in it to talk to the network or talk to the display or the keyboard or mouse. And as you can see, well, this is good because it basically makes now my tasks to be predictable. Now they're not interrupted. But two more benefits of this. You can actually estimate precisely how long it takes for you to do data transfers because you're pooling basically, right? Every time a task needs to do I/O, it pools because you cannot do interrupts. Without interrupts, your only way of dealing with I/O is pooling. So you can definitely pool for as much as you want and then stop pooling. So there is a precise timing for you. You can estimate exactly how long each data transfer takes. And the other good thing about it is that you don't need to change anything inside your kernel, right? Because now tasks are dealing with their I/Os. Kernel is not doing anything. Kernel has set aside and let the tasks deal with I/O and such. So there is no change if you want to add a new device. The kernel doesn't need to do anything. Well, the bad thing about it, though, is that now you're degrading the performance of your CPU because of polling, because polling is wasting time, right? You're just, if you have infrequent events in your I/O, you're basically wasting CPU time. The second problem with this approach is that now you have to have very, very rich device logic in all your tasks. And let's say you change a device or you add a device to your system. Now all the programmers have to go back and reprogram their tasks and their applications. So what are the other options? The second option is, as before, disable interrupts. Again, don't let interrupts happen. Only keep the timer interrupt. But instead of putting the I/O device logic in all tasks, put them in a specific kernel routines. So write function calls inside kernel that would deal with I/O, and then periodically, like set a timer, let's say, every 1 second, every 1 millisecond, every 1 microsecond, whatever, wake the kernel up and run these routines. And what do these routines do? They basically pull, again, on the device, on I/O devices, to see if there is any data. And if there is, then they will deal with it. Now, what are the good things about it? Again, because we have disabled interrupts, we don't have to deal with unbounded delays. The execution time of these periodic routines can be estimated as before. So before it was inside the tasks, now it's in the kernel. But again, I can basically estimate how long it takes. And the benefit over the previous one is that now I have a modular design where the hardware details don't need to be leaked into the tasks. They're just all isolated inside kernel. Now, the bad things about it is that I haven't dealt with the performance degradation of the performance because I'm still polling, and that still wastes CPU time. I'm busy waiting for the CPU. The other bad thing about it is that now I have to modify the kernel every time I add or remove a device or upgrade a device or whatever. So now the kernel has to change, which sometimes is a big deal. You have to recompile the entire kernel, you have to change. And in some cases, you can't change the kernel on fly. You have to basically shut down the entire system and bring the system up again in some cases, some extreme cases. And the third one is now the communication. If a task wants to do I/O, has to go through multiple hubs. And you would definitely need some more inter-task communication compared to the first one. The first one, each task does its own I/O, but now you have to go to the kernel and then come back to your devices, and that actually adds some inter-task communication and delay. What is the third option? So the third option is we really cannot keep the interrupts disabled and do anything about the performance degradation. If you really don't want to deal with the performance degradation, you have to let interrupts happen. So you enable interrupts this time, but in order to write, instead of writing interrupt handlers that are rich and do a lot of things and could take a lot of time, you could reduce your device drivers and interrupt handlers to the least possible size. So they do as little as possible. What they usually do, which is very similar to what we had with the bottom half and top half, is that these device drivers and interrupt handlers in real-time systems, they activate other tasks. So they either create a new task or wake up a new task that is already running in the system and give it a new instruction to do based on the interrupt that happened. So all they're doing is basically sort of message passing of some sort that, oh, this thing happened, now it has to be dealt with. And that's it. That's all it does. And then the operating system treats these device driver tasks that are now either created or woken up like the other tasks in the system. They also have their own deadlines, and they all dealt with how other tasks are dealt with. They don't have higher priority than others. They could actually, but not generally speaking. So you can actually predict and have some guarantees for your system, because now all you're dealing with is a bunch of tasks and very lightweight interrupts. So compared to the previous ones, we have eliminated busy waiting, so no performance degradation anymore because we have enabled interrupts. The other thing about it is that we don't really need to do any changes inside our kernel. We're delegating the task of dealing with interrupts to the device drivers. But the cost we are paying is that, first of all, there is some communication, again, compared to the first one between the tasks and the device drivers to transfer data. This is sort of minimized now, right? It's not as high as it was with the second option, but it's not as low as it was with this first option. And the second cost that we're paying is we're still dealing with unbounded delays. So we still might have unbounded delays because we're still dealing with unexpected device driver handling. But the cost and the probability of that happening has been reduced dramatically, because now we don't have really long interrupt handlers. We have made them as light as possible, and that's the advantage of this model. And by the way, this is basically, I think, as far as I know, this is what many real-time operating systems do. So it's the third solution that is used usually. Okay, so the next stop for us is to talk about memory management. This slide is kind of like futuristic in the context of our lectures. We'll have series of slides and lectures on memory management coming after, actually right after this, the lecture on real-time systems. So I'm going to deep dive into this, but just to give you all the things that you need to know about real-time system, I have put it here. So just listen to these. Even if you don't get everything here, you can come back to it after we finish memory management and virtual to physical address translation later on in the course. Then you can come back to this slide and probably get a lot more out of it than what you could at this point. That being said, this slide basically summarizes the next 4 or 5 lectures that are coming. So in one slide, I'm just summarizing all of it. So in general purpose operating systems, what usually happens is that you want protection for your processes. And as you could remember, we used memory mapping or address mapping and address translation for this. We give each process a separate virtual address space, and then we translate those virtual addresses, to physical addresses. Now, in order for us to do this efficiently, what usually general purpose operating systems do is that they divide the memory into pages. Both the virtual memory and physical memory is divided into pages, fixed size pages. I got a question. So what would be the difference between the solution 3 and using top-bottom driver halves in general purpose operating systems? It's a good question. So the general idea is the same. It's kind of like how you implement them, because with top and bottom halves, you still could do a lot in both of them. So your bottom half or your top half could still be doing a lot. They don't really create new tasks. They manage everything inside themselves. What we're suggesting here with this methodology in solution 3 is that instead of doing any sort of logic or algorithm there, instead of implementing anything specific, just create a new task so that that new task can go and deal with it. Even if that new task is to, let's say, initiate a DMA. Don't do it yourself. Create a new task to do the DMA stuff, or create a new task that copies data between the memory and buffers inside devices. So just do the minimal amount of work to wake up a new task or to create a new task to deal with the issue you have. So that's the main difference. Hopefully that answered the question. Okay, so we're talking about memory management. Now, with these pages, what address translation becomes is basically translating these virtual pages to physical pages. We want a mapping to tell us where to find each one of these virtual pages inside our physical memory. Both of them are paged, so we just want a mapping between virtual pages and physical pages. Where this is stored is usually called page table. So we have page table inside our memory system. We'll talk about it in details, where we store these mappings. Now, going to these mappings and finding these translations usually takes a lot of time and introduces a lot of overhead. So as a result, many modern hardware and processors, they have cache close to the processor to cache these address translations. So if I have already translated virtual page 2 to physical page 5, I can cache this translation so that if in the future I see this address again, I know the translation. I don't need to go back to the memory again. So this cache is very small, as you could imagine, and it's called translation look-aside buffer, TLB, in short. So many operating system many modern architectures have this, right? Now, what is the problem with this? The problem with TLB is the problem we had with caches like before, when I started talking about microarchitecture. Caches introduce non-determinism. If you hit in the cache, if you can find the translation in TLB, then your address translation is very fast. But if you can't, then you have to go to the memory to get that address translation. Now, this is fine in a general purpose system, but in a real-time operating system and real-time system, this basically costs you predictability. Now, one possible solution that actually many real-time operating systems and real-time systems do is to just avoid having virtual memory. So just deal with physical memory. As we will talk later, this introduces a huge inflexibility in the system and could cause a lot of security risks. But this is sort of fine with most of real-time systems, and partially with, generally speaking, with embedded systems, because usually real-time systems are owned by a single user and are written for a single task. Let's say that, the electronic engine. So you really don't mind the security risk because you're the only user in the system. You're writing all the tasks. Everything belongs to you. So you're fine with it. You don't really need the isolation, sort of. It would depend, right? But in many cases, that is something that people are willing to pay. Now, the other problem with everything that I said above is something that we will also talk about, which is called paging. What usually happens in our systems is that our processes think that they have a lot of memory. The virtual memory space is big, but usually the physical memory is small, depending on how much RAM, how much DRAM you have in your system. As a result, operating systems do something that is called paging or demand paging. And basically what that is we use the memory as a cache for disk, right? So basically all the pages, all the virtual pages for each process can be kept inside the disk, in the hard disk, in the permanent storage. And every page that the process actually needs and uses, we bring them to memory. Once the memory is full, and we don't have a space anymore, and some process wants to access its pages that are not in the memory, we have to evict a page that is already in physical memory, write it back to the disk, and bring the page that we need. And as you can imagine, this process is absolutely time-consuming. Writing an entire page back to the disk and bringing a new page back. And this is actually the same way. Now, if memory is acting like a cache for disk, caches always provide non-determinism. So one way to deal with this whole thing is to just pin your pages. Tell the operating system that you cannot evict this page. So if you have a real-time task with deadlines, you can basically pin all the pages for this task to the memory and tell operating system you're not allowed to touch these. These are not evictable. And that way, you're sort of sure that you're not doing paging on the memory of this task. And that kind of like mitigates the problem you have with paging. Okay. The other aspect to consider is programming languages. One of the aspects of programming languages is dynamic memory operations, which is basically what you did with Lab 1, allocating the heap. One of the big tasks of any language and any library to manage a program is to allocate memory as needed dynamically. Now, if you have looked into the lectures that were shared with you for Lab 1, you probably have seen these terms about fragmentation. And the reason that dynamic memory is not something that we want to have in a real-time system is because it's usually unpredictable. As you saw, hopefully, and implemented, to allocate memory, we usually implement some heuristic, best fit, first fit, or a worst fit. So there are heuristics to use. Now, the execution time of that algorithm to find a memory for the requested, let's say, malloc, is non-deterministic. So you could find the space right where your free list starts, or you might have to go through the entire list to find the place that you need, right? And that is non-deterministic, how much it takes for you to find that memory location. And since most of these are heuristics, they usually cause or lead to suboptimal allocations. And what that causes is basically fragmentation. Here is an example. So let's say you malloc three memory blocks, and you basically look at your free memory here. I think I have 10. You allocate the first 3 to this pointer. P1 becomes the pointer to the beginning of these 3. Then let's say you do another malloc in your application, and you request for 4 extra blocks. And again, we're lucky, we can just get it right away after that 3 allocated ones. Then let's say you free P1. So now P1 is freed. That memory is now available. Now you initiate a new malloc for 4. And as you can see in this case, you have enough space to allocate, but they're not contiguous. And as a result, you cannot basically answer this request, and it would fail. So even though you have free memory, you cannot serve this request. And if you think, oh, I can, defragment, I can move those 4 allocated ones to some other place and make a space for the new request, that is really not possible because P2 could have been copied, right? You might have different copies of P2, all of them pointing to that fourth block, and the library has no means to track how many copies of P2 have been created. So if now I move that memory, all the previous copies would be pointing to something that is not valid anymore. So it's not an option to defragment at this point. So all of this basically is non-determinism, unpredictability as a result of fragmentation and running optimization algorithms. So one possible solution to deal with this whole thing is to, instead of allowing allocation of different sizes, you could make a fixed size memory blocks and allocate those. So let's say you could divide your memory to whatever you want, and at each time everybody can just request one of those blocks. This causes more fragmentation, usually internal fragmentation, which we will talk about a lot in more details in the memory section of this course. But that probably, you could imagine, if let's say I have this 10 units, I can say, okay, I divide it into 2 units of size 5. So even if this guy needs 3, I'm going to give it a 5 unit. And that basically means that 2 units are not going to be used, 2 bytes or whatever that unit is, but which is internal fragmentation. But that's sort of fine as long as I can prevent external fragmentation. Another solution which is widely used in real-time systems is to just prevent dynamic data structures. So many real-time systems do not allow dynamic memory allocation. So whatever memory you need, it has to be statically allocated. It gets flexibility away from your system, but at least it gives you predictability. The other aspect when you're talking about programming languages is recursion. This is also something that is highly unwanted in real-time operating system and real-time systems, because you could get infinite loops. It's really hard to guarantee anything if you have recursion and you don't know, and the number of recursions depend on an input or data. So if the number of recursions is determined dynamically, then there is no way for you to guarantee anything about the execution time, and it becomes unbounded. And there are examples of real-time programming languages with some or all of these features. You have real-time Java, and some other real-time programming languages that you can potentially look into. Okay, so what time is it? I'm going to give you 2 minutes, and then we'll start talking about scheduling. Okay, we're back. Let's go ahead with scheduling. So, as I alluded at the beginning, for general purpose schedulers, the goal is to minimize some sort of average system throughput. But for real-time systems, we're more interested in tasks and each individual task. So we're talking about now minimizing a worst case response time for each task. And as I mentioned, predictability is not equal to fast computing. When we're talking about real-time tasks, there are different types of real-time tasks. The one that we mostly focus on is periodic tasks. So periodic tasks, each periodic task is a set of jobs that arrive at fixed period, let's say P. And each job has a worst case execution time we call E, and it has a hard relative deadline that is usually less than, it has to be less than P. And if it's not mentioned, if we don't say anything about a deadline for a periodic task, you should assume that the deadline, the relative deadline, is basically P. It's the period. And then we define utilization for each task. So a utilization of a task is the execution time, the worst case execution time of its jobs divided by its period. So the jobs inside periodic tasks are basically identical. Identical jobs coming periodically. And each one of them will take some worst case execution time if you wish. So this is how we show T7-4. The first one is the period. So every 7 time units, a job comes, and each job will take 4 units, worst case. And then the relative deadline, when you don't mention it here, is basically 7. So you have to finish your task by the time that the next one, you have to finish this job by the time that the next job comes. So the relative deadlines becomes the period. Now there are other types of real-time tasks. You could have periodic tasks that basically come randomly and they don't have hard deadlines. You can have sporadic tasks that come randomly but have hard deadlines. When you talk about set of tasks, then your tasks could be independent or they could be dependent. Your tasks could be preemptible or non-preemptible. Okay, so now that we know about tasks, let's talk about scheduling and terminology for scheduling. The first class of schedulers are basically static schedulers. So static schedulers, they assign a priority to each task, and the priority of a task never changes over time. So one example is rate-monotonic scheduling, which we will see. Then you have dynamic schedulers. So dynamic schedulers, instead of giving priority to each task, they give priority to each job, and the priority of a job never changes. But as you can see, because tasks have jobs that are arriving over time, so a single task could get different priorities because its jobs are getting different priorities. But each individual job, whenever it's assigned a priority, that priority never changes. And an example of this is earliest deadline first, which we'll talk about. Then you have fully dynamic scheduling. So these ones, you're assigning priorities to jobs but that priority could actually change over time. So it's the most flexible one. And an example of it, which is latest laxity first. Sorry, least laxity first scheduling, LLF. So we say a scheduler S is feasible if it so if we're talking about, sorry, a schedule. If I give you a schedule of tasks, then you can say it's feasible if all tasks meet their deadlines. Now, a task is a schedulable under a scheduling class C if there exists a scheduling algorithm A in C that produces feasible schedule for T. And finally, a scheduling algorithm A is optimal with respect to a particular class of schedulers if it produces feasible schedule for any schedulable task set T under C. Now, the first question that comes up, do we need to really talk about now real-time scheduling? We have talked about so many different types of schedulers. We talked about, you know, you name it. We saw a lot of schedulers for uniprocessors. Do we need to talk about specific now schedulers for real-time scheduling systems, the real-time systems? Let's see an example. Let's run round robin on this workload. So here I have 3 tasks. The first one has a deadline, has a period and deadline of 2. The second one period and deadline of 5. The third one period and deadline of 10. And each job of T1 takes 1 unit. Each job of T2 takes 1 unit, and each job of T3 takes 3 units. So these are the arrival times of jobs for each one of these tasks. So somebody's asking, what is the difference between task and job? So basically, task is the high level unit that we talk about. And if you have a task, a periodic task, a task that has a period, then in order for us to distinguish between different arrivals of this task, we call each one of them a job. So a job is each instance of the task. Kind of the way to look at it is maybe the task is the class and job is the instance or object when it's periodic. So if you don't have a periodic task, then task and job are the same because there is only one instance of the task. It's not periodic. It's not coming again and again and again. It just occurs, it arrives, and then it departs. But if you have periodic tasks, then in order for us to distinguish between every time that this task arrives, we call each one of those arrivals a new job. So that's how we're distinguishing between jobs and tasks. Okay. So here, as you can see, these are the deadlines and arrivals. Now let's do round robin. So everybody, all the tasks have arrived at the beginning. So everybody is here. So if we want to do round robin, you do 1 unit of T1, 1 unit of T2, 1 unit of T3, right? Now you have to go up. This task only required 1 unit for this period. Now at this time, a new job has come with execution 1, so I can run that job and meet the deadline, so everything is fine. This second one doesn't have any new job because it only needed 1 execution time unit during this period, and we've already finished it. So there is no job left for T2. we're good. So we just jump to T3 and do 1 unit of T3 here. Now at this point, we are going to go up again. A new job of T1 has come. We can execute it. Now at this point, T2 also has a new job, so we can execute it. Now we come back to T3. Now we have to go back to T1, but as you can see, we've already missed the deadline for this job, because in this period, we were supposed to run a job from T1, and we were not able to meet that deadline. So we missed the deadline here. So by just running round robin, we easily missed the deadline for T1's job. Now, let's talk about real-time scheduling policies. We start with a static one, which, if you remember, rate-monotonic was an example of a static scheduler. So what it does, it just, we're going to make some assumptions. We're going to, for now, focus on tasks that are periodic and independent. And we know their execution time, their worst case execution time upfront. So all is known. Now, how do we allocate? How do we schedule? We're going to give high priority to, so we're going to give priority to tasks. Remember, it's a static. So we're going to assign priorities to tasks, not jobs. And we're going to give higher priorities to tasks that have shorter periods. So if you have a, so the shorter your period is, the higher your priority is. And then these are going to be fixed for tasks. We're not going to change anyone's priority. This is a point that I'm going to just make without any proof. You're going to believe me. So rate monotonic, go back and look at the definition of optimality, but it is optimal with respect to static schedulers. What this line means is, if you have a static scheduler that produces feasible schedules for a workload, then rate monotonic also can produce a feasible schedule for that workload. But again, if it's optimal with respect to static schedulers, not dynamic, not fully dynamic. So among static schedulers, rate monotonic is optimal. Again, go back and see the definition of optimality. Now let's see how it works in action for the same workload that we saw with round robin. So again, I have the same tasks, the same deadlines, the same arrival times. So in this case, T1 gets highest priority because it has the lowest, the shortest period. Its period is 2. So T1's jobs, every time they come, they get the highest priority. They have to run first. And then T2 jobs are the medium priorities, and T3 becomes the low priority task because it has the longest period. Now let's look at it. So at this point, T1 has a job. So because it has the highest priority, we will run T1's job. Then T2 job has the highest priority, we run it. At this point now, again, T1 has another job. T3 has a job. So between T1 and T3, we choose T1 because T1 has the highest priority. Once we are done with this, at this point, only T3 has a job. So we run 1 unit of that. Again, at this point, T1 has a job. So we have to because it has highest priority, we'll run that one. Now at this point, T2 and T3 have jobs. We run T2s because it has higher priority. Again, T1, then T3, again T1, and T3. And because the tasks are periodic, so this will repeat what you just saw, because, yeah, so 10 actually is the greatest common multiplier of 10, 5, and 2. So this will just repeat again and again. And we're able to meet every task's deadline. So rate monotonic worked in this case. Now, rate monotonic doesn't work all the time. Here's another example. So in this case, I have 3 different tasks with these properties. And here I have just marked the periods. Now T1 has highest priority, we run its job. Then at this point, T2 and T3 have jobs, and T1 doesn't have any job. So we run 2 tasks, 2 units of T2's job. Then at this point, T1 has a job, so we have to run T1's job. And then we go back. So now we're done with T1, we're done with T2, T3, we can run 1 unit. Then at this point, T2 again has a job, we run it. T1 has a job, we run it. And at this point, we come, T2 still has a job that we can run. T3 also has a job, but because T2 has a higher priority, we're going to run T2's job, and by doing so, we'll miss the deadline for T3. So as you can see, rate monotonic failed to schedule this workload. So one task missed its deadline. In general, we have this theorem, which I'm not going to prove, but we're going to take it as is. It says that, let's say you have n periodic tasks with execution time EI for each one of them, and deadline and period PI for each one of them. Then rate monotonic is guaranteed to produce a feasible schedule if the total utilization, so EI divided by PI for each task, is its utilization, if you remember. Now, if I sum up the utilization of each task, if this sum is less than or equal n times 2 to the power of 1/n minus 1, then Rm is guaranteed to produce a feasible schedule. Now, for different n's, this bound n times 2 to the power of 1/n minus 1 is something like this. So as you increase n, this bound reduces. I think it gets to 0.67. So one point to note here is that this condition doesn't say anything if this sum is more than this value. So if the cumulative utilization is more than this bound, then we have no guarantees. This doesn't mean that Rm will fail. It could still produce a feasible solution, but it could also fail. There is no guarantee. But if it is less than this number, then Rm is guaranteed to produce a feasible solution. Now, if you look at the example we saw in the previous slide for these 3 tasks, if I sum up the utilization of T1 is 1/3, the utilization of T2 is 2/5, the utilization of T3 is 2/8, and in total, that's 98.33% utilization. Now, if this should be 0.98, so this is percentile. It's a typo. Let me fix it. Okay. Now for 3 tasks, so if n equals 3, then if n equals 3, then 3 times 2 to the power of 1/3 minus 1 is 0.78. And as you can see, the cumulative utilization is more than this number. As a result, there is no guarantee. And in this particular case, it was the case that RM actually failed to produce a feasible schedule. Now, this will lead us to the next class of schedulers, which is dynamic scheduling. Now we're going to assign priorities to jobs instead of tasks. And the way the one particular scheduler that we're going to look at is called earliest deadline first. I got a question. I'll answer that question once I'm done with this earliest deadline first. I'll go back to that question. Sorry. Let me finish this. So earliest deadline first. How does it work? We're going to assign we're going to assign priorities to each job instead of tasks. Now we're going to give higher priority for jobs with earlier deadlines. So the sooner your deadline is, the higher your priority becomes. And the fantastic thing about EDF, earliest deadline first, is that it's optimal with respect to all online schedulers. So any scheduler, any online scheduler that can produce a feasible schedule for a workload means that EDF also can produce a feasible scheduler for that workload. So that's the power of EDF. Now let's look at an example. So I'm looking at the example where rate monotonic failed. So this the example that we saw that rate monotonic failed. So in this case, at the beginning, I have T1's job with a deadline that is 3. T2's job has a deadline 5, and T3's job has a deadline of 8. So between these 3, T1's job has the earliest deadline, so it gets the highest priority. So it runs and it finishes. Then T2's job has highest priority. It runs. Now at this point, I get a new job in my system. So T1's job again comes, and it has a deadline of 6. So if I compare this deadline with T3's job, which the deadline here is 8, T1's job has a earlier deadline, so it gets higher priority. So I run T1's job. Now at this point, I don't have any task in a job in the system, so I run T3. Now here, T2 also will have a new job. It's arrival of T2's job. Now I compare T2's job and T3's job. T2's job's deadline is 10. T3's job's deadline is 8. So T3's job gets higher priority, so that one runs. Now I'm done with T3. At this point, T1 has a job. Then at this point, nobody has a job but T2, so I run T2. So at this point here, T3 also will have a job, but then because its deadline is 16, whereas the deadline of 10 for T2, so T2 has priority, it runs. Now, at this point, I run T1 and so on and so forth. So there is a guarantee that earliest deadline first produces a feasible schedule for this task. Okay, I'm so sorry I ran out of time, but I at least finished earliest deadline first. Now let me answer the question that was posed. So I got a question. So to fit the definition of optimality, we don't consider tasks that don't hold on that condition to be schedulable in the static scheduling class. That's a loaded question. So if I go back to the definitions, okay, so all you care about are these three. So first of all, you should know what a feasible schedule is. A feasible schedule is a schedule that under which all the deadlines are met. That's the definition of feasibility. That definition is about a schedule. Now, for each task set, for each workload, we say it is a schedulable under a class of schedulers. Let's say here, if we focus on, let's say, static schedulers, for each set of tasks, we could say this task is a schedulable under a static scheduler class if I can find one scheduler inside this class that can produce a feasible schedule for this set. And if that doesn't exist, so if I have a task set that no scheduler inside this class can produce a feasible schedule for, then I say, okay, this task set is not schedulable. And if it's not schedulable, then it doesn't come into the definition of optimality. Because in the definition of optimality, we're going to just focus on a schedulable task sets. So for optimality now, we say a scheduling algorithm is optimal with respect to a class if it can produce feasible schedules for every schedulable task. Basically, what that means is if there is another scheduler in this class that can produce a feasible schedule for this task, then I can also do it. If that's the case, then I'm optimal, which is the case with rate monotonic. So in rate monotonic, we say if there is any other static scheduler that can produce a feasible schedule for any task set, then rate monotonic can also do it. And with earliest deadline first, we say if any. So one thing I had to mention, all three of these classes are online schedulers. We don't talk about offline scheduler because that's not very interesting. So offline scheduling means that you basically schedule offline, nothing changes online. You have basically a table of tasks where every task is a schedule. Nothing is dynamic. But among online schedulers, then earliest deadline first is optimal, meaning that if there is any scheduler that could produce a feasible schedule for a task set, then earliest deadline first can do it too. Okay, so sorry, I went too much over time answering that question. It was a good question though. So look for the announcement for the quiz. Get started if you haven't already on Lab 3, and hopefully talk to you on Friday. Thank you for those who attended, and take care, be safe, and bye.